Hello everyone, myself. Today we are going to solve the given problem. Problem is based on Jacobians. Here in the question, if u is equal to x plus y plus z plus t and v is equal to x plus y, once again, and v is equal to x plus y minus of z minus of t and w is equal to xy minus of zt and r square is equal to x square plus y square minus of z square minus of t square. Then show that del of u comma v comma w comma r upon del of x comma y comma z comma t is equal to 0 and hence find the relation between them. Let's solve the problem. Given u is equal to x plus y plus z plus t and v is equal to x plus y minus of z and minus of t and w is equal to x y minus of zt and r square is given by x square plus y square minus of z square and minus of t square. We have to show that del of u comma v comma w comma r upon del of x comma y comma z comma t. We have to find del of u comma v comma w comma r upon del of x comma y comma z comma t. It is given by in the determinant, that is del u upon del x and del v upon del x, del w upon del x and del r upon del x. For y, that is del u upon del y, del v upon del y and del w upon del y and del r upon del y. For z, that is del u upon del z and del v upon del z and del w upon del z and del r upon del z. For third, we have to, for t, that is del u upon del t and del v upon del t and del w upon del t and del r upon del t. We have to find the value and put in the determinant to further solve. First, we have to find del u upon del x. U is equal to x plus y plus z plus t differentiating partially with respect to x, that is del u upon del x, that is here is x differentiating partially with respect to x, that is 1. For further, we have to find del u upon del y, del u upon del y. Del u upon del y is given by again y differentiating partially with respect to y, that is 1, and del u upon del z, del u upon del z. Again the value of u partially differentiating with respect to z, that is z differentiating partially with respect to z, that is 1. Further, we have to find del u upon del t. Del u upon del t, again the value of u partially differentiating with respect to t, that is also 1. Further, we have to find del v upon del x. Del v upon del x. The value of v partially differentiating with respect to x, that is 1, and del v upon del y, del v upon del y. Again the value of v partially differentiating with respect to y, that is also 1, and del v upon del z, del v upon del z. Again the value of v partially differentiating with respect to z, here is minus of z, differentiating partially with respect to z, that is minus of 1, and del v upon del t. Again the value of v partially differentiating with respect to t. Here is minus of t differentiating partially with respect to t, that is minus of 1. Further we have to find del w upon del x. Del w upon del x. The value of w partially differentiating with respect to x, taking y as a constant. So we have to differentiating with respect to x, that is of y, and del w upon del y. Again the value of w partially differentiating with respect to y, taking x as a constant, that is x, and del w upon del z. Further, again we have to differentiate the value of w with respect to z, taking t as a constant. Here is minus of zt, differentiating partially with respect to z, that is minus of t. Further, we have to find del w upon del t. Again, the value of w partially differentiating with respect to t, taking z as a constant, that is minus of zt, differentiating partially with respect to t, taking z as a constant, that is minus of z. Further, we have to find del r upon del x. The value of r differentiating partially with respect to x, that is r square is 2r del r upon del x is equal to 2x, and from here 2 to 2 is cancelled out. Then the value of del r upon del x is x upon r. Further, we have to find del r upon del y, that is del r upon del y. Again the value of r differentiating partially with respect to y, that is 2r del r upon del y is equal to 2y. From here 2 to 2 is cancelled out. Then the value of del r upon del y is y upon r. Further, we have to find del r upon del z, del r upon del z. Again the value of r square differentiating partially with respect to z, that is 2r del r upon del z minus of 2z, and from here 2 to 2 is cancelled out. The value of here is 2r, 2 to 2 is cancelled out. Then the value of del r upon del z is given by minus of z upon r. Further, we have to find del r upon del t, and del r upon del t is given by again the value of r square differentiating partially with respect to t, that is r square is 2r del r by del t is equal to minus of 2t, and from here 2 to 2 is cancelled out. Then the value of del r upon del t is given by minus of t upon r. We have to put the value of r once again. R square is equal to x square plus y square. We can put the value of r once again. Some misprint in the question, I think. I will check the question. here in place of r square, this is the r is equal to, so we have to find one del r by del x, that is 2 is not present, that is 2x, this is 2x, and del r upon del y, del r upon del y is, once again, del r upon del y is also 2y, and del r upon del z, this is also minus of 2z, and del r upon del t is minus of 2t. Some misprint in the question. Here is r is equal to x square plus y square minus of z square and minus of t square. We have to put the value in the given determinant, that is, we have to write here, that is del r upon del t is equal to minus of 2t. Putting the value here, that is determinant of, first we have to put del u upon del x, that is 1, and del u upon del y is also 1, and del u upon del z is also 1, and del u upon del t is also 1. Further we have to put the value of del v upon del x. Del v upon del x is 1, and del v upon del y is also 1, and del v upon del z is minus of 1, and del v upon del t is minus of 1. Further we have to put the value del w upon del x. Del w upon del x is y, and del w upon del y is x, del w upon del z is minus of t, and del w upon del t is given by minus of z. Further we have to write del r upon del x. Del r upon del x is given by 2x, and del r upon del y is given by 2y, and del r upon del z is minus of 2z, and del r upon del t is minus of 2t. Further we have to solve the determinant. Further we have to solve the determinant. Further we have to solve the determinant using the operation, that is r1 replacing r1 plus of r2. Once again, this is r1 and this is r2, this is r3 and this is r4. We have to take operation r1 replacing r1 plus r2. Further we have to write, that is determinant of r1 plus r2, that is replacing 1 plus 1 is 2 and 1 plus 1 is also 2, and from here 1 plus 1 and minus 1 is 0, and here is also plus 1 and minus 1 is also 0, and r2 is unchanged, that is 1 comma 1 and minus of 1 and minus of 1. Further, that is y x minus of t and minus of z, and this is for 2x 2y and minus of 2z and minus of 2t. Further we have to solve on taking operation. This is column C1 and this is column C2, and this is C3, and this is C4. We have to take operation C2, C2 replacing C2 minus of C1, C2 replacing C2 minus of C1. Further we have to write, that is, here we have to write C2 minus C1, that is C1 is unchanged, that is 2, 1, y, 2x, and we have to change in C2, that is C2 minus of C1, that is 2 minus 2 is 0, and 1 minus 1 is also 0, and from here x minus y, and for here that is taking 2 common, that is y minus of x, y minus of x, and C3 is unchanged, that is 0, 0, and minus of 1 and minus of 1, minus of t and minus of z, and from here minus of 2z and minus of 2t. Further we have to solve once again. Further we have to solve when expanding the determinant with respect to C1, that is 2 determinant of, when expanding with C1, then this and this part is neglected, then the remaining is 2 times of 0, this is neglected, and this is, then remaining is 0 minus 1 minus 1, 0 minus 1 and minus 1, and here is x minus of y, x minus of y, and here is minus of t and minus of z, minus of t and minus of z, and here is 2 times of y minus of x and minus of 2z, minus of 2z and minus of 2t. Further we have to solve this determinant on taking operation, that is minus of 1 and minus of 1, once again C3, this is C1 and this is C2 and this is C3. We have to take operation here, that is C3 replacing C3 minus C2. We have to take operation, that is C3 minus C2. Then the determinants becomes C1 is unchanged, that is 0 and x minus of y, and we can also write the y minus of x, that is minus of 2 x minus of y, and we have, and C2 is also unchanged, that is minus of 1 and minus of t and minus of 2z. We have to change in C3, that is C3 minus of C2, that is C3 minus of C2, when taking, that is this is 0, minus of 1, that is C3 is minus 1, and minus is already present, that is C2, that is this is 0, and for this is minus of z, minus of z is C3 and minus of C2, that is plus of t, minus minus is plus, we can write that is t minus of z, and for this that is minus of 2t, minus of 2t, and minus of C3 minus C2, that is minus minus is plus, plus of 2z, and we can also write taking 2 common, that is z minus of t, and we can also write that is from here t minus z is written as minus is taking common z minus of t, and we have to take common this is C1 and this is C2 and this is C3. We have to take common C1 from taking common from C1 from C1 is x minus of y, and from C3 we have to take a common z minus of t, and C3 from z minus of t. Further we have to write the determinant, then we have to take common x minus y, and 2 is already present, that is 2 times of x minus of y. X minus of y is taking common from C1 and z minus of t is taking common from C3, that is z minus of t, and the given determinant remaining is here is 0, and from here we have to take common x minus y, that is 1, and from here that is minus of 2, and C2 is unchanged, that is minus of 1 and minus of t and minus of 2z, and from here we have to take common z minus t, that is 0, 0 and minus 1, and here is plus 2. Once again minus of 2, then 0, we have to 0 minus of 1 and 0, 1 t, t is missing here something, x minus of y minus of 2t, t minus of z, z minus of t. Zero minus of 1, we have to take common from C1 is minus of x minus y. When taking common, once again here is minus, and we have to take common minus, from here we have to take common minus x minus of y, C1, that is 0, and from here is minus of 1, and minus of 2 is present, that is taking minus x minus of y common, that is plus of 2, and from here this is C1, C2, and this is C3, and we have to know if C1 and C3 are same column. If the two columns are identical in the determinant, so we have to the value of Jacobian becomes 0. We have to expanding, we can also find the value of 0, del of u comma v comma w comma r upon del of x comma y comma z into t is equal to 0, and if you expand we can also find, and we have to also write if the C1 and C3 are identical. So we have to know if the two columns are identical, then the value of the covariance are 0. Further we have to write, that is, this is the value is, this is equal to 0. We have to show that, and further we have to find the relation between them. We have to find the relation between them. We have to show that this is proved, and further in the given question said, hence find the relation between them. Then u is equal to x plus y plus z plus t, and v is equal to x plus y minus of z minus of t, and w is equal to xy minus of zt, and r is equal to x square plus y square minus z square minus of t is given. Then we have to find the relation between them. We have to write, that is, u into v, that is x plus of y plus of z plus t, and v is, that is, x plus of y, and minus is taking common once again, z plus of t. And from here we can also write, that is, this is also taken into curly bracket, and this is, from here we have to know, let this is a, x plus y is a, and z plus t is b, and from here that is x plus y is a, and z plus t is b, and we know the following relation, that is, a square minus of b square is given by a plus of b and a minus of b. We follow the sequence a plus b and a minus b. Then we have to write, that is, uv is equal to x plus of y ka square minus of z plus t ka square. Further we have to expand, that is, uv is equal to, and open x plus y ka whole square, that is x square plus y square plus of 2xy, and one second, x plus y, this is a, one second, some mistake has happened, one second. We have to write a minus b ka whole square, a plus b and a minus b, that is a minus b ka whole square, that is a minus b ka whole square, a plus b and a minus b. Then x plus y, a plus b, and a minus of b, a plus of b. We can also write, that is, x plus y ka whole square minus of z plus t ka whole square. Further we have to expand, that is x square plus y square plus 2xy, and we can also expand, that is z square plus t square plus 2zt, and from here that is x square plus y square plus 2xy, and minus of z square minus of t square minus of 2zt, and we find the relation, that is, from, one second, we have to take, that is, uv is equal to x square plus of y square and minus of z square and minus of t square, and we have to take plus of 2xy and minus of 2zt in one bracket, taking 2 common, that is x plus y minus of zt, and we have in the given the value is here, that is uv is equal to, the value of r is given x square plus y square minus of z square minus of t square. Here x square plus y square minus of z square minus of t square, we have to put the value, that is r, and plus of 2, and the given value is w is equal to xy minus object t. We have to put the value of xy minus object t, that is 2w. This is the required relation between the uv, w and r. Thank you class, and thank you for watching. If any doubt, kindly comment in comment section.